Welcome to example number 12. It's a fairly complicated problem. I might have to break up the video into two pieces. So we're going to start off by doing part A, part B, and C, and then maybe do D in a separate video. We'll see how things go. So in this question, I have a capacitor combination of capacitors. 1 and 2 are in parallel with each other, and then that combination is in series with capacitor 3. We are given capacitor 1 is just C, capacitor 2 is 5 times that, so 5C, and the next one third is 3 times C. So in part A, what we're asked to figure out is what is the equivalent capacitance of this circuit, right? So when we solve for equivalent capacitance problems, what we do is we start off with the innermost pieces. We're going to basically add these two capacitors in parallel with each other first, and then rewrite or redraw our circuit with basically two capacitors instead. So we'll combine these as one capacitor. So we need to find the equivalent capacitance, all right? We need to find the equivalent capacitance of basically C1 and C2. And if you recognize, these are in parallel with each other. So the equivalent capacitance in parallel is basically adding simply the capacitors. So in this case, it will be C plus 5C. So our equivalent capacitance in parallel will essentially be 6C. So then the next thing we want to do is basically redraw the circuit, if you can imagine, with just essentially one capacitor that represents the capacitance of 1 and 2 together. So I've just redrew the circuit and replaced essentially 1 and 2 with this new capacitor that is just 6C. So now what we're going to do is we're going to find the equivalent capacitance of the whole circuit, right? All right. So we're of essentially C1, 2, and C3. So these are in series. So the capacitance formula in series is 1 over C equivalent equals 1 over C1, 2 in this case, and C1 over C3. So we put that in here. All right, we will get 1 over 6C plus 1 over 3C. And you've got a common denominator of, I guess, 2. Sorry, not 2, but multiply top and bottom by 2. So 6C. And so you will get 2 plus 3, 1 here, which gives you 3. So this gives you an equivalent capacitance of 2C. And that's the answer for the first part. I'll just put a box around it. That's part A. Okay, so now a little bit trickier part. We need to rank the capacitors according to the charge from largest to smallest. So maybe I'm going to just do this on another page here. Okay, so we now move on to part B. All right, and I'm going to have these two drawn circuits here just to help discuss what's going on. So what we need to remember is some rules about capacitors in series and capacitors in parallel. So when we have capacitors in parallel, and in this case that would be C1 and C2, we know that their voltages, all right, are equal to each other. So voltage 1 and voltage 2 are exactly equal to each other. When you have capacitors in series, so in this case that would be C1, 2 and C3, we know that they will have the same charge. So the charge of 1 and 2 will be the same charge as 3. Okay? So that's sort of, I guess, one rule for each one. Let's go to a second rule here. All right? When you have capacitors that are in parallel, again, we know that their charges will add up. All right, so the charge of 1 and 2. So imagine that this had like just one single positive charge with a negative charge. And this was like 5 times that. So I'll put 5 little positive and negative charges on here. So the charge of 1 and the charge of 2 must add up to the total charge. And that would actually be equal to as if you had essentially one single capacitor, which we've called it C12. Well, this charge here, 1, 2, would be the same as taking charge 1 and charge 2 and adding them up, right? And then because charges are in series are equal to each other, you can rewrite this, I guess, and say, well, 1 and 2 is just really 1 plus 2, right? And I just realized, by the way, this is not 1, 3. This is just simply 3 here, okay? So charge 1 and 2 would be equal to, oops, actually, no, that's right. That's the same as charge 1, 2 to combine, right? But then in the end, that's also equal to charge 3, because we know that they're in series with each other. So charges 1 and 3, 1 and 2 are equal to charge 3. So in that, replacing 1 and 2 with 1 plus 2 would be equal to the charge of 3. So kind of like what I'm writing over here on the other side. In series, we also have another rule. So we know that in parallel, the charges add, but in series, the voltages add. So if you were to hook up a voltmeter here, and call that, I don't know what you want to call it, voltage 1, 2, and then you were to hook up another voltmeter here, voltage 3, these two voltages will add to the total voltage across the battery. So the EMF, which is really, this is, you could think of it as just the total voltage of the entire circuit, is equal to voltage 1, 2 plus voltage 3. Okay, so we're going to kind of have those ideas hopefully straight in our head as we continue to now try to figure out if we can rank the voltages and also rank the charges. So we're kind of doing, I guess, part B and C together. All right? So let's, to make things easier, perhaps we call Q1 just simply Q. And what we want to know what Q2 is in terms of Q. And then we also want to know, like you could think over here, right? We want to know what Q3 is in terms of Q. So what is Q3? Okay? So we're going to use those rules. So we're going to just assume that. And another important formula that might be helpful here is that C is equal to Q all over delta V. So we're going to also use that to help us as well. All right, where to start? This is always a little bit tricky here. So maybe I'll start with the idea of the easiest equation. Maybe charges or voltages are equal. Let's start with voltage 1 and voltage 2 being equal to each other. Okay? So we know that's true. And then if we rewrite this equation, putting voltage by itself, we would have charge all over capacitance. Charge over capacitance. But we want to do it for that particular capacitor. So charge 1 over capacitance 1, charge 2 over capacitance 2. And remember what we called Q1, essentially Q, right? And then C1 we're just going to call C, because that's what it is. And then Q2 we'll write Q2, but instead of C2 we're going to put 5C. And you'll see some cancellations, and essentially Q2 is equal to 5 Qs. So it has 5 times the charge of charge 1. Okay? So I put 1 positive sign here, and then like there are 5 positive signs there. It's 5 times that, right? Now, what about the third capacitor here? Actually, how many? What would its charge be? And I made a mistake here, and you may notice it. I have a total of 6 here. Actually, I put 5 here, but it's actually 6. Why? Because remember, charges add. So this is 5 plus 1, 6, and there should be 5 negative signs. And then consequently, this should be 5 and also a negative. So hopefully you're going to get the idea. I want to show that essentially capacitor 3 has 6 times the charge of number 1. So how are we going to show that? Perhaps we'll use this equation here. We're going to use Q1 plus Q2 is equal to Q12, which is in series with third capacitor, and they have to have the same charge. So then Q1 plus 2, Q1 and Q2 must add up and be equal to Q3. Q1 we said is just Q, and we just learned that Q2, if you recall down below here, is 5Q. So therefore that makes Q3 is equal to 6Q. So now we have it. We have Q3 is 6Q, Q2 is 5Q, and Q1 is just simply Q. So we can now rank it and say that Q3 is the largest charge, followed by 2, followed by 1. And that's the answer for part of it. Okay, that would be part B, I guess. The next part is the voltages, right? Now, we already know part of it. We know over here, I'll use a little different highlighter here. We know that the voltages are equal in parallel. So we already know the answer of that 1 and 2 have the same voltage, right? But how does 3 compare to that, right? Well, we know that the voltages add up to be equal to the EMF, right? So let's start off with the idea that, I'll use purple here, voltage 1 and voltage 2 are equal to each other. And there's probably a lot of different approaches, so I'm just going to think here. Perhaps I'll use charges. Q1, 2, remember that capacitor of equivalent capacitance of 1 and 2 together, must be the same as Q3 because they're in series with each other. And we know that Q can be written as C times delta V. So we'll write C12 times delta V12 is equal to C3 delta V3. And C12, if you recall, we calculated that as 6C delta V12, and then C3 is 3C, and then delta V3. So therefore, the voltage 3 is essentially twice the voltage of 1, 2. Remember, voltage 1, 2, by the way, is the same thing as just voltage 1 or 2. So therefore, voltage 3 is either twice voltage 1 and also twice voltage 2. Okay, so then we can now rank the voltages and say voltage 3 is the greatest, and voltage 1 and voltage 2 are equivalent to each other because they're in parallel with each other. Okay, and that's it so far in the video. We've answered part A, part B, and part C. All right, might make more sense if you had just the sign values and just calculated stuff, but I kind of want to be able to solve this conceptually as well. All right, the video is already long, but I will attempt here to discuss what would happen if C1 was increase. How would everything change? Now, I suppose one of the ways you could do it is to just change the value 1. You could say, like, suppose C1 is now, instead of C, but it's like 4C. Okay? And then the new equivalent capacitance of 1 and 2 would be 9C, because we would just add them up, 4 plus 5. And then the equivalent capacitance of the circuit would be 1 over 9C plus 1 over 3C. All right? If you multiply this by 3 over 3 here, then you'll get 4 over 9. So then the equivalent capacitance would be 1 over 4/9, which would be 9 over 4 times C. And so hopefully you would see that the equivalent capacitance originally was just 2C, right? And now it's like more than 2C, right? It's essentially 2 1/4 C. So the new equivalent capacitance is greater than the old capacitance. Now, I don't know if you need to really go through all that. You could kind of just argue it this way. You know, capacitance is given as epsilon naught A over D if you had a, say, a vacuum-filled one. And when you increase the capacitance, right, you're, like, say, just one of them, you're making, like, the plate larger. Like, you're just increasing C1. Then effectively you're making the whole capacitance get bigger because you're making one plate larger. So then that therefore makes capacitance 1 and 2 larger, and then has an effect on the whole capacitance getting bigger. All right. I'm not sure if that helps. Maybe just work you through the math, you could see that. But essentially, the total capacitance increases is what I'm trying to say. Now, we also know that equivalent capacitance is equal to the total charge, right, divided by the voltage. But the voltage, by the way, is the EMF, which is not changing, and so we see that the total capacitance is increasing, so that means that we have more charge. So the total charge, right, of the whole circuit increases. Okay? So that means that now if we were to draw this whole circuit, we have more charge, right? There's more negative charges. Before, remember, I drew like something like 6 negative signs here, right? But now I'm going to add another negative sign here, right? Why? Because there's more charge total, so there's going to be more negative charge on that bottom plate of that C3. So essentially Q3 increases, because Q3 is the charge on capacitor 3 is the same as the total charge of the whole circuit, right? So that means then Q1 and Q2 together, right, will increase. All right? So 1 and 2 increase, right? But does 1 increase? Does 2 increase? Do both increases? Does one go up, one go down? Right? That's a little bit trickier to explain. But we know that the sum of Q1 and Q2 have to increase because, remember, Q1 plus Q2, which is equivalent to Q12, is equal to Q3. And if the charge of 3 goes up, then 1 and 2 technically go up, and then these together go up. But we don't know by who goes up more, or what. Yeah. So I could draw like bunch of positives here, like instead of 6 before, but have 7, let's say, right? But we don't know how that distributes, right? Sorry, I'm trying to redraw it here. Okay, on here, how do these 7 charges redistribute here, right? Okay, so perhaps we talk a bit about voltage, and we're out to get about charge. If we were to put a voltmeter across 3, right? And then we have a voltmeter across 1 and 2. We will note that the voltage of 3 will change, right? So if you recall, capacitance equals charge over voltage. The capacitance 3 hasn't changed at all. But we know its charge has changed, right? Because the total charge of the circuit has increased. So the voltage 3 is equal to charge 3, right, divided by capacitance 3. But charge 3 has increased while the capacitance has remained constant, right? So therefore, voltage 3 has increased. We have an increase in the voltage. But voltage of 1 and 2 plus the voltage of 3 have to add up to that EMF, the battery voltage, and that's not changing. So that voltage of the battery is remaining constant. Well, I just found out that the voltage 3 had gone up a little bit. So in order to accommodate in keeping the total voltage the same, then the voltage across 1 or 2 has to not remain the same actually, to go down. So our conclusion here is that we've not really asked that, but voltage 3 increases, and voltage 1 and voltage 2 decrease. Okay, so now we just need to answer what happens to the charge. So the charge of 2 would be equal to the capacitance multiplied by the voltage. Capacitance 2 and voltage 2. And remember that, again, this has to remain the same. Capacitance 2 is remaining the same. And we just determined that the voltage of 1 and 2, which by the way, 1 and 2 is the same as voltage 1 or voltage 2 because they're in parallel. So voltage 2 has decreased, therefore charge 2 has to decrease. So now we know Q2 decreases. Okay, so our last piece is we've got charge 3 going up, charge 2 going down, and what happens to charge 1, right? So how do we answer that? So my first thinking was perhaps I just use the same formula and say Q3, or not Q3, sorry, Q1 is equal to C1 multiplied by voltage 1. And then ask myself, well, what happened to each of these things? We know that the capacitance increased, actually by what I wrote originally 4 times that amount, but then the voltage decreased, but they did decrease by the same factor, right? They're not necessarily increasing one by 4 and decreasing the other one by a fourth, and therefore the charge doesn't change. Actually, Q does change. So this is not going to work out because the problem is you got 2 things changing, and you have to kind of think of it a little bit more deeply. So perhaps we just look at the equation Q1 plus Q2 must be equal to Q1 and 2, or Q3. And we know that the charge of 3 has increased, and therefore the charge of 1 and 2 have increased. But we just found out that Q2 has to decrease. So in order for these two to add up to a number that has increased, then we know that Q1 has to increase. So our last answer here is charge 1 increases. So to summarize, Q1 will increase, Q2 will decrease, and Q3 will increase. Now, quick point here, you might find it helpful to go to PhET and muck around with this kind of simulation. Here's a little simulation in here. Maybe can't quite see the whole thing, but if I change this to multiple capacitors, right, over here, no, it's not working there, unfortunately. Let me pause. Yeah, there's the PhET capacitor lab, and I'm just going to go down to multiple capacitors and then select down here 2 in parallel and combo with 1 in series, and there you have it. And then you can kind of muck around with here and put in one capacitor and another capacitance, change the capacitance around like this, and then give it some voltage, right? You can add a voltmeter in here and kind of go through and sort of conceptually see that there's the voltage across that capacitor, that's 0.6 volts. And then there's the voltage across that capacitor, that's 0.9 volts. But then if I were to somehow increase the capacitor 2 here a little bit more, you'll see that the voltage is doing what? It's decreasing a little bit, right? Did we do that? Okay, actually it's increasing, sorry, on the top one. Anyway, you can play around with this app. Anyway, the video is quite long. Might as well end it here. All right. Hopefully this all makes sense.